the talk on prompt engineering, which Dr. Amar Azad from IBM gave. The first part was given by him. Now, today we are continuing with this discussion, and Dr. Rudramurthy, who was our student and currently in IBM, will continue these discussions. Now, the importance of this particular topic cannot be overemphasized. The community is understanding that supervised machine learning is not the way. Okay, because creation of data is very expensive, and it also creates human bias in the data. I think supervised learning will gradually be fading out. So we need other methods of interacting with the machine and training it. And prompt engineering, of course, is not training, but showing large language models how to do something with small number of examples. That is the attractiveness of prompt engineering. And over to you, Rudra.
Thanks, sir. Good morning, everyone. Today I'll be talking about prompting large language models, mainly focusing on discrete prompting. Yeah, just to give an overview, right? So in the previous session, Amar gave a broader view of prompting. So we did not go into the details of prompting. We just looked at different types of prompting like discrete prompting, continuous prompting, multitask prompting, etc. So in this particular session, I'll just focus mainly on discrete prompt engineering. So in the next session, Amar will focus more on continuous prompt engineering, multitask prompting, and some research questions with respect to prompting. So that's the agenda. Okay. Now, why prompting? So for example, so this graph I borrowed from papers with code. I'll just add the source here. So if you look at the F1 score on English Ontonauts named entity recognition data, right? Say 2014, when people were mainly focusing on feature engineering and deep learning, uh, it was still in its early stages with word embeddings and so on. The F score was around 84, and then came a BiLSTM CRF architecture by Chio and Nichols and BiLSTM CRF, which gave a significant improvement in the F score. And then with the large pre-trained language models, we see the F1 score has saturated around 92. So yeah, fine-tuning large language models on the downstream task, it has shown very impressive performance. But the question is, yeah, fine-tuning helps, but can we know what the language model, what's the knowledge which has already embedded in the knowledge model? Sir, before I begin, has the recording started?
Oh, okay, okay. Sandhya, have you started the recording?
Yes, sir.
Oh, okay, right. Thank you.
Thanks. Yeah. Why prompting? So basically, the reason for prompting is we want to know what information the language model already holds. So can we query a large language model with a prompt similar to the way we ask humans and get some information out of it? Now the question comes, how should we formulate the query? So that's the overall idea behind prompting as a field. So in this particular session, I'll be focusing on two main papers. So this is the first paper. How can we know what language models know? So this was published in 2021 in Tackle. So the main idea or the main motivation why I chose these two papers is this particular paper is very intuitive when it comes to creating prompts. And the next paper, which is auto prompt, it shows it brings up the question, where do we, I mean, it pushes the boundary of how do we define prompts. So when someone says prompt engineering, where do we stop? So that's the reason for choosing these two papers. Now let's begin with looking at the first paper. How can we know what language models know? Yeah. So when prompting work began, people started creating manual prompts. For example, Barack Obama was born in, and basically they queried these large language models. So basically replacing this dashes with a mask in case of bird, and let's say the bird model was able to predict Honolulu or Hawaii, and so that's how manual prompts came into picture. But the main disadvantage is how can I construct these manual prompts? Also, the prompts can be suboptimal. The reason is, I mean, the language model, it learns or acquires the knowledge from the training data it has seen. However, in the training data, the knowledge might have occurred in some other context. So, for example, instead of a sentence of the form Barack Obama was born in, so in the data or the language model might have seen information like the birthplace of Barack Obama is Honolulu, Hawaii. So when we query such a large, such a language model with this particular prompt, Barack Obama was born in, then the model will fail to predict the correct answer. So in this paper, they give an example. So for example, there is this manual prompt. DirectX is developed by, and this is the label which we need to predict using, say, BERT model. And they also list the top five predictions um, and the corresponding log probabilities. Here you can see Microsoft appears in top two, but not as the top one. However, if we can rephrase this prompt, instead of querying it as DirectX is released by, or we can say that X released the DirectX, you can see Microsoft appears in the top one. Similarly, there could be another prompt which says DirectX is created by. Now replacing developed with created also led to the model correctly predicting Microsoft as the top one answer. So yeah, this is the main motivation with respect to this work. So instead of manually writing prompts, can we say search for prompts which can extract the relevant information from the language model? So the main contribution of this paper is they look at two approaches to finding better prompts. The first approach, they follow a mining approach, and the second approach is a generation approach, and they show the benefit for the task of knowledge retrieval. Now, um, what is the task of knowledge retrieval? So here the task is to retrieve factual knowledge from the language models. So for example, looking at the same example, right? Barack Obama was born in Honolulu. So here we have Barack Obama as the subject, born as the relation, and Honolulu is the object. Now I can represent this sentence as a triplet, subject, relation, and object, X, R, Y. Now the goal of knowledge retrieval is to find the object given the subject and the relation. So given Barack Obama and born, I need to find Honolulu. So that's the goal of knowledge retrieval. Now, uh,
Uh,
where, yes,
Hey, Rudra, this is Amar
yeah,
here. I just wanted to bring in some point here. Uh, so I think the larger question here that one might ask is, by doing prompting, are we trying to retrieve the facts from the knowledge? Basically based on knowledge, or we are trying to basically manipulate or understand how language model understood about those knowledge, right? So
yeah,
what is the right way to understand that? What we are doing here by prompting?
yes. So in this paper, they're mainly focusing on retrieving the factual knowledge. Uh, we'll also look at auto prompt. In auto prompt, they are not trying to retrieve the factual knowledge. So basically, they are trying to find out what is the best prompt to retrieve and knowledge, not just knowledge, to manipulate the language model in retrieving the result we intend to.
Right, right. Maybe we can say this that language model, when they're trained, they actually have, in some form, they actually store or basically learn the knowledge from external, world, or maybe the data set what is exposed to, but they have a different biases about the knowledge, and that creates a situation where you might not be able to get the right factual knowledge based on worldly knowledge, and for that to happen, you want to, by doing prompting, you want to basically handle the biases what language model has. Is it right way to say?
Uh, Sorry, Amar, can we define bias here? Because And the term bias with respect to language model has
So for
become
example,
that,
like here, right, you gave a couple of examples before that, right?
yes.
So for the
Let me
same
go.
question, actually,
Yeah. DirectX is developed by X released the DirectX and DirectX is created by. Yeah, Amar.
yeah, if you look at this example here, no?
Yes.
So it looks like that I mean basically the knowledge what one should have from the data is DirectX is developed by. Sorry, I think this is something just two-step paraphrasing, is it? Or there's something wrong here?
No,
One
Amar.
second.
So this is the first one is the manual prompt, and the next two prompts are the ones which they mine and which they get from paraphrasing. So I'll be talking about these two approaches later.
Okay, so what I was trying to say, many times you actually, I think there are some examples which you might also be showing that you might not get the right answers by just doing some prompting. And for that, you might want to manipulate the prompt such that you get the right answer from that. And that actually means that the model was actually is biased towards certain types of prompt only, and that's what people do with auto prompting and all prompt mining kind of work, right? That's what I was trying to bring in by the bias.
Yeah, Amar, true. So Amar, actually the continuous prompt engineering and prompt-based fine-tuning have kept it for the next session.
Sure, sure, yeah. Please
Because
continue.
yes, yeah.
Yeah, I have Rudra. Sorry to interrupt you there. I have one
Hi,
question here.
Saiful.
One ba-
Yes,
one basic question I have is that whatever relations that we're extracting from the prompting, uh, will they be affected by the kind of prompt that we give? Because, for example, relations can be of many types, and
yes.
so, whatever relations that we give in our prompts, only the output of prompting will only include those relations, or will it also include the relations that we haven't defined in the prompts? What What are the observations there?
Sorry, Saiful. I got confused a bit. So you're talking with respect to this particular task, right? Downstream task, knowledge retrieval.
Yes, yes. So
Okay.
here we can see there are triplets X,
Yes.
Y, and R, where R is the
Yes.
relation between Barack
Yes.
Obama and Honolulu, right?
Yes.
For example, what I'm trying to ask is that I'm giving some prompt as an input, and
Yeah.
I'm basing that prompt. Taking out some relations, some triplets out of my test sentence. Okay, so
Okay.
the relation that I'm taking out of my test sentences, will they be limited by the prompt I have defined?
I Yes. So that's the reason why, I mean, the overall goal of this particular task, right? How
Yeah.
do we find better prompts which can define the relation?
Okay, so so we can, even if we haven't defined some kind of relations in the prompt, uh, we can even mine those relations which are not defined in the prompts. Is that the right understanding?
Mm, Okay, let me finish off the approach, then we can revisit this. I hope that once we talk about the approach, you'll get answer to the question.
Sure, sure.
Sure. So the task is, so even though the task is to find the object, given the subject and the relation. So in this particular paper, they try to figure out what is the best prompt text or what's the best relation, which when provided with Barack Obama leads to the generation Honolulu. Now, the overall goal is to find out this prompt text. So in manual prompting, what we do is we look at the subject and the object and say, okay, Barack Obama was born in. So was born in is a prompt text. Now, instead of creating such manual prompts, we want an automated way of figuring it out. So for that, yeah, they in the paper they propose two approaches. One is mining based generation and the paraphrasing. And mining based generation is very intuitive. So basically what you do is I know the subject and I know the object. I know Barack Obama and let's say Honolulu, Hawaii. So basically I'll look at all Wikipedia sentences which contains both the subject and the object. Now, what intuitively if I can find, so basically the words between Barack Obama and Honolulu will define the relation between them. So words within the vicinity of X and Y, they form my relation. So this is my prompt text. So, but this need not be the case always, right? So for that, they also look at dependency-based prompts. So they pass the sentence through a dependency parser and then basically extract the root verb which connects both the subject and the object. And why they do is because these middle word prompts, they cannot capture prompt text of this form. Honolulu is the birthplace of Barack Obama. So is the birthplace of, this is my prompt text. And in this case, the subject and object, they're interchange, right? It's not of the form X relation Y. So in this way, they extract various prompts. And the another approach which they follow is this paraphrasing based generation. Basically, they employ back translation to generate more prompts. So given the original prompt, let's say Barack Obama was born in Honolulu, they translate this text to say German. And from German, they translate it back to English. Now, once they translate it back to English, so there's a good chance that the model might not generate the original input sentence, which is Barack Obama was born in Honolulu. So in this way, they generate prompt candidates. And what they do is, in order to rank the prompt candidates generated, they rank it based on their round trip probability, and top T prompts are considered. So any questions with respect to these approaches? Say mining based generation and paraphrasing based generation. So the approaches are very intuitive. Given X and Y, subject and object, you search a very large corpus for all sentences containing X and Y. Now, whatever word appears between X and Y forms your prompt text. So that's the middle word prompt approach. And in dependency based prompts, basically what you do is you pass the sentence through a dependency parser. Now, say look at all sentences where Barack is the, you get the subject object and you also get the root verb, and then use the root verb as the prompt text. And paraphrasing is given the original manual prompt, you translate it to other language, and once you translate it back to English, you get a set of prompt candidates and use them as your prompts. Okay, so till now we have extracted candidate prompts, but we haven't evaluated how good the prompts are. So for that, what they do is, so how to select a prompt from a given set of candidate prompts. So what you do is you give the subject and the prompt text and see if the model predicts the correct object. If the model is able to predict the correct object in say top one, then the prediction is correct. So in this way, what you do is you rank the candidate prompts. So basically what they do is they take a very small set of data which they call as train data. Let's say 100 instances with labels. Every candidate prompt is applied on this 100 example set, and you calculate the accuracy with respect to this prompt candidate, and you repeat the same procedure for all the prompts. And now you can rank the prompts based on their accuracy score and select top K prompts. So that's how they perform the prompt selection. So given a set of n candidate prompts, you apply the prompt on a small set of instances, calculate the accuracy for each prompt, and choose the highest or the top K prompts. Now, with this approach, you're not just restricted with say one prompt. You can be, you might be left out with say 10 prompts or 5 prompts. Now, how do you apply? So do you choose, say you apply all the 5 prompts and choose the best one? So for that, they go with two approaches. One is rank-based ensemble and optimized ensemble. In rank-based ensemble, they apply the K prompts individually and they average out the log probabilities, and then they get the prediction. And in optimized ensemble, what they do is each of the log probability is assigned a weight, and you optimize this particular weight. So you are assigning a weight for each prompt. So this is the approach defined by the paper, and they show the results on factual knowledge retrieval. So they compare the results with BERT base and BERT large. Here, man refers to the results obtained from manual prompting. So this is the baseline. where you have a prompt created by a human, and now you have prompts from mining, you have prompts from paraphrasing. As you can see, with mining, there's a small improvement in the micro average F score, 31 to 31.4. But as you increase the number of prompts, so instead of looking at top one prompt from the mining, top three and top five, there's a jump. And when you optimize the weights, you get 38.9. So basically, Oracle is, you can think of it as a skyline. Even if one of the prompt gives you the best answer, then you consider it as a match. The prediction is correct. So with optimizing, they are able to get 38.9. Now, what happens if you combine the prompts obtained from mining with manual prompt? You again observe improvements. Similarly, if you combine mining prompts with paraphrasing, you also observe improvements. So the same with manual prompts and paraphrasing. Say 31.1 to 34.1, just adding prompts from paraphrasing. Similar observations are made on BERT large. So I won't go through the results on BERT large. I'll just look at BERT piece. Now, in the paper, they also show some of the prompts obtained with, say, mining or paraphrasing approach. So if you look at the relation religion, right, the manual prompt is of the form X is affiliated with the Y religion. However, when mining, they find out if they give the prompt in this template, X who converted to Y, that resulted in a plus 60% accuracy gain. Similarly, place of death, right? X died in Y. Instead of this manual prompt, X died at his home in Y. 4.6% improvement. Subclass of X is a subclass of Y. X is a type of Y. Position held, X has the position of Y. X is elected. So, for example, position held, say this mind prompt, right? X is elected. It need not be the appropriate prompt for this particular relation. But as you can see, replacing as the position of with is elected leads to some accuracy gains. So indicating that a manual prompting is always suboptimal, and whatever results you get from manual prompting, it shows a lower bound on the knowledge encoded in the language model. And also they do provide say some evidences of optimized prompting, right? So in this case, they have three prompts for the relation owned by X is owned by, X was acquired by, X is division of Y. So with their approach, they saw that around 0.485 weight was assigned to X is owned by, so major contribution from this particular prompt. Then 0.15 contribution from these two prompts. X was X was acquired by, X division of Y. And also if you look at relation, right? X who converted to Y, but in this case, it does not make sense. Y Tirthankara X, and it has a weightage of 0.19. So yeah, so basically what this table says is it's counterintuitive, and what we feel is the best way to encode prompts need not be the best way in which the language model has acquired its knowledge. We might think that X is represented. Hi, Niyar.
So I just have one quick doubt. So in order
Yes.
to improve the accuracy, are not we changing some facts? Let's say religion is the relation. Maybe the
Yes.
religion the person has acquired by birth only. By changing the prompt to who converted to, we were like changing the meaning, like he converted or she converted after birth, right? So that's the meaning has already changed in the mind prompt.
Yes, Niyar, that's true. So
But
yeah,
that's not ideal, right? We just should not go by the accuracy to change the fact.
yeah. So in this case, we are not changing the fact. So basically, it's a way of looking at how the say information is encoded in the language model, right? So this is one way of looking at the results from this paper. We feel that say X
Okay,
is
so
affiliated
these
with
are
the,
the
yes, Niyar.
please continue.
Yeah. Say for
What you
example,
were
right?
saying? Please.
Yeah, if someone follows a particular religion, and we feel that that particular information is encoded via the phrase follows. X follows religion Y. But the model has not acquired that, or it does not encode the information using that phrase, but it's encoding the information using something else. Say who converted to Y. So this also gives us some insights of how language model encodes information. As you pointed out, yes, in this particular case, who converted to Y as a negative connotation and is not the ideal prompt which we want to obtain
That's
for
a
the religion.
harmful effect actually from the language model.
Yes. So with that thing, probably, we could look at why the language model is encoding this information using this particular prompt.
So actually, isn't this a very bad example to pick in the sense that it runs really badly into common sense issues, because most people in the world don't change their religion. And if you have to predict the the religion of a person, the best source is not to look for any conversion cases. The best source is somewhere else, right? Like
Yes.
English language. I mean,
Yes.
any language is very deficient in common sense, because if you go by English corpus, most sheep are black; they are not white.
Yes.
All carpets are red, right?
Yes.
So this is a particularly poor example for them to pick in the paper, I think.
True.
By the way, these are mined from some data set, right? Using some data set, right? So
Yes, Amar. So these
are
are
these
from
coming as an artifact of data set, selection of data set as well? Any discussion about that?
no, Amar, they haven't discussed that. But I mean, as they mentioned in the earlier slides, right? Sorry, let me go back. So the mining is obtained from Wikipedia. And yeah, I mean, English Wikipedia contains a diverse set of sentences and it's a pretty large corpus, right? Compared to Wikipedia of any other languages.
It's really weird that in Wikipedia you're getting, no, I think it's not only because of Wikipedia. It might be also which works best with the language model. So it's the artifact of
Yes.
both actually.
Yes, it's
So this is the problem. What I was saying is like, it's like we are trying
Definitely a problem with bot model.
that's what the bias actually model has, and that has come through the corpus what it has seen, right? I mean, although this may
yes,
not be this may not be the, what should I call it, like real truth or real knowledge, but this is how it actually happens.
yeah, so we could say
But
this.
in some sense, see, in Wikipedia, so this is an interesting statement from the point of view of Wikipedia, right? So somebody is entering it, and this is some information that they want to put for a person. In that sense, the language model, while learning, it might have picked up this cue that this is also, religion,
Exactly.
sort of
Yeah.
getting sense. So this is an artifact of data. It looks like.
I doubt that this is the only thing in Wikipedia might be available, but the language model, while optimizing this, chooses that as a with higher value, right? So that is also coming through the language model as well.
Right.
Yes, Amar. So I believe this is an artifact of the language model rather than Wikipedia. I mean, I do agree Wikipedia might contain some instances of who converted to and so on, right? But if this prompts are chosen such that on an average it gives the best performance for this particular religion relation. That means, so basically we are looking at the language model and asking, if I give this prompt text, how likely are you to retrieve the correct object in this case? So this is the bias in the language model.
Maybe we can keep the dataset same and change the language model to see what kind of prompts are being mined by different language models.
Yeah, Near. So
That
in
would
this paper, they also look
give
at
us better idea.
yeah. So in this paper, they also look at Roberta, but they don't provide the prompts which work the best for Roberta model. So here the
Robota
prompts
bot dataset, training dataset was pretty much same, no?
yeah, it's pretty much same, but and the training there is some differences in the way they train.
Training before sleep.
Yes.
Yeah, yeah.
So we just the
So,
way we
so,
train.
so let's say the data that we have used to learn the prompts, in that data set out of 100, if 70% people are those who has really converted, then that's how it has come. It looks like that, right?
So Sapan, when you say data, are you talking about the data for mining or data on which the language model
Data,
is?
no, data for mining.
Yeah. So let's say who converted to Y is
No,
occurring
Sapan,
regularly.
that may not be. Sorry, just so Sapan actually, once you see the lower one, right, where you say the weightage that is coming, that is coming from the language model, right?
Yes.
So what language model is actually giving you an output, based on that you find the weight, and you see that it's clearly showing that 0.615, something like that, right?
Yes.
Right.
So that is the artifact. I mean, even if you had one example saying that I belong to, say, like Hindu, right?
Mm.
I mean, I'm
Mm.
just giving very weird example. And language model would have understood that during training, that I belong to Hindu is a good example for that.
Mm.
Or my religion is Hindu, right? So then it would have given some weight to it, or some good amount of weight to it, right? But it's clearly showing that language, it's because of language model that's coming out.
Yeah. So to further add to Amar's point, right? See, you have three candidate prompts here who converted to Tirthankara and dedicated to. So out of these three prompts, I would say dedicated to is an appropriate prompt, but the language model is assigning weight of 0.11 for it, but 0.615 for X who converted to Y. So it's an artifact of the language model, the biasness in the language model, not the data.
Well, yeah, I'll need to think more on this.
Sure, Sapan.
Actually, that raises a very big question, actually, because prompting is becoming one of the very important method to do a lot of NLP tasks going forward. A lot of work
Right.
is getting on, and that is very much driven by the understanding or knowledge. I should call knowledge of the language model, and it's clearly that in many, not this is the one example, but you will see down the line there are many examples where language model doesn't look like possess worldly knowledge very clearly. It's in many places it's a highly biased, highly weird. So what is going on actually? By prompting, we are trying to basically get into and understand about the language model, or we are trying to make NLP work better. That's a very big question. I think this is very bigger question for NLP community to ask about. But that's something which people will be dealing very soon. I think I am sure that very soon a
Right.
lot of work will come to actually explain the biases in the language model through prompting.
True, Amar.
Yeah, true. I can't agree more. Yeah, true.
Yeah. So even though much of the literature on prompting focuses on few shot learning or zero shot learning, right? But prompting goes hand in hand with, say, other approaches like adversarial attacks on large language models, understanding bias in language models. So it's not just about performing few shot classification or zero shot classification. It's also about understanding how language models encode data and how do we retrieve it. So yeah. So going to the next one, right? Yeah. So they also see are prompts transferable across different models. So for that, they look at cross-model performance, say transfer of prompts from BERT base to BERT large and BERT to earning. So what they observe is BERT base to BERT large, there's not much of a drop. If I use the prompt obtained from BERT base and use it on BERT large, whereas there is some drop in performance. If I choose a prompt which works best for BERT, may not work the best for earning model and so on. And also another observation which they make is, see, when you look at manual prompts, right, you don't have to try to generate prompts. Some minor changes in the prompts can also lead to significant improvements. So for example, instead of putting the question as X place in Y position, if you replace the preposition in with that, X place at Y position, that leads to an accuracy gain of 23%. X was created in Y versus X was made in Y, around 10.8% improvement. So yeah, yeah. So basically, the goal of this paper was to show that manual prompts are always suboptimal. It always gives you a lower bound on the knowledge present in the model. So better prompt engineering will always lead to significant improvements. Now we look at the other extreme. So this was a 2020 NLP paper, auto prompt eliciting knowledge from language models with automatically generated prompts. So this paper I have included in this presentation because this particular paper pushes the boundary of prompts and leads to some very interesting questions about how language models encode information. Okay, yeah. So yeah, existing literature, it either looks at manual prompt creation or it tries to mine for better prompts. So instead of writing prompts or going with mining based or paraphrasing based approach to create better prompts, can we have an automated way of creating prompts for any task? So that's the motivation for this particular work. And the approach is very simple. So you have a sentence and the task input, and you have a set of trigger tokens. As of now, I've just shown 4 tokens, and you have the predict token. So predict token is your mask symbol in case of BERT-like language models, and you try to predict the class label for this particular sentence. So for example, if you want to do the task of sentiment analysis, right? This is the input. I like this movie, and you have a set of trigger tokens. Let me talk about trigger tokens a bit later. And you have the mass token. Now what you do is you look at the probability distribution, output probability distribution on the word mask, and see that, say, amazing as this probability, wonderful as this probability, good as this probability. And there's a way of figuring out these label tokens. And then what you do is you do an aggregate. Similarly, you do an aggregate over all the label tokens for the negative class. And then finally, you make a decision whether the sentiment of this particular sentence is positive or negative. Okay. Now the question comes, how do you define this trigger token? So these trigger tokens define my template prompt, my prompt. So in order to do that, what they do is they initially assign to some, say, mass token. They take a batch of example and do the forward pass on this batch. Now, once they have done the forward pass, basically what they do is they look at the embedding of this trigger token and look at the backpropagated error and see what if I change this particular token with some other token, or does it impact my overall log likelihood? So what I want to do is I want to choose those which results in the largest increase. And they do it iteratively until the model converges. So any questions with respect to this particular trigger search? So basically this approach is inspired from adversarial attacks. So in adversarial attacks, basically what you want to do is you want to replace some of the words with another word, which ensures that the model, instead of predicting the label correctly, mispredicts. So they apply something similar for finding the trigger tokens. And after
just a quick.
Yes, Amar.
So these are the candidate tokens which are actually kind of like before the sentences, is it? What you are basically questioning there? Prompts before. Okay, here is sentence and then
these are the trigger tokens, Amar. So basically,
So
trigger. Yeah.
Go on.
These are the set of words or prompts which I need to append to the input so that I get the required prediction.
So when you say that actually your model is getting converged, what do you mean by model is getting converged?
So when I say model is getting converged, I'm looking at this log likelihood, change in the log likelihood. So when I replace this particular mask, say this is the first position for the template word, right? Prompt word. So if I replace mask with say rating, the change in the log likelihood is very minimal. So that's my conversion criteria.
But that is, so this is basically you have a set of word which is these words are coming from vocabulary or some
Yeah,
set
these
of
words are
words.
coming from vocabulary.
So in some sense you're searching, right?
Yeah, I'm searching in the vocabulary space
Mhm.
and seeing what tokens or what words to add to this trigger tokens place so that the model say predicts the correct sentiment.
Yeah, it's basically combinatorial search, right? It's purely,
Yes,
right? Okay.
yes,
Okay.
it's combinatory. Yes. So this was for
Okay.
the trigger search.
But this might be
Now,
very expensive from terms of searching, no? I mean, compute.
yes, Amar. They
Okay.
do mention in the paper that it is computationally expensive.
Okay. Okay.
Yeah. So we have looked at how to get the best trigger tokens, but we haven't looked at how to get the best label tokens because more often than not, when I give the sentence, I like this movie, what is the sentiment of the movie? Let's say with manual prompt, the output will be positive or negative. That's very unlikely, right? The output on the mass token would be either good, bad, and so on. Now, how do we generate these label tokens for every in a task agnostic way? So that we don't have to incorporate the domain knowledge into this. So for that, they also give this algorithm to figure out the label tokens. So what they do is they train a linear classifier on top of the mass token representation. Once they train the linear classifier, so they have got a representation for every class label. Now and the parameters of the BERT model is frozen. It is not updated. Only the parameters of the linear classifier is updated. Now they look at the label representation and calculate, say, the dot product with uh, the output layer representation for every token and select the top k tokens. And with such an approach, what they find is for the task of sentiment analysis to define positive class, if the um, prediction turns out to be Chris, marvelous, or philanthrope, then it contributes to the positive sentiment. Whereas for the negative class, worse, incompetence, and worse contributes the most to the negative class. Yeah, with respect to negative class, these label tokens make sense, but with respect to positive tokens, they do not make sense. So why does say the mass language modeling giving me philanthrope as one of the top k tokens indicate that the sentence has positive sentiment? It doesn't make sense, but this is what the model discovers. Okay, now let's look at how the results look like. So they have compared it with, say, the earlier BiLSTM models, BiLSTM with Elmo embeddings. Linear probing is just training a linear classifier. Fine tuning is fine tuning the entire, all the parameters of the BERT model, same with Roberta. And what they observe is, if I look at BERT manual, say the F score is around 63%. However, when I perform auto prompting, discover the best prompt, the performance improves to 82.3. Similarly, Roberta with manual prompt, the F score is 85.2. However, with auto prompt, the F score is 91.4. There's a significant jump, and the performance from Roberta model is almost comparable to, it clearly outperforms BiLSTM and Elmo embeddings. It's close to what we get from fine-tuning a BERT model. Now, sorry, let me just connect my laptop to the charger. Hi everyone, sorry for the inconvenience. And if you look at the trigger tokens learned by the Roberta model, right? For the sentiment analysis task, you have the sentence and the trigger tokens are atmosphere, a lot, dialogue, clone, totally. And then you have the mass token. So basically what it says is for any input sentence, when I concatenate with atmosphere, a lot, dialogue, clone, totally, and pass it to the Roberta model, And if this is my mass token, it very accurately predicts the sentiment. However, this does not really make sense, right? Why should concatenating atmosphere, a lot, dialogue, clone totally to the sentence help the model predict the correct sentiment of the input text? We look at some more examples in the upcoming slides. So similarly, they also, yeah, Amar.
So one more question. So I do understand that what they have shown is the best. They are the best combination of word, which basically combination of word which predicts gives the highest accuracy, right?
Yes, Amar.
Did they do some analysis that maybe closer to, because what they are selecting is basically top from the rank of the words which are having the minimum gradient, right?
Yes, Amar.
Or maximum likelihood, right? So
Yes.
did they have some do they have some analysis where actually not the top one in the rank, something which actually makes sense to human but may not make too much difference in the accuracy,
No,
some hit
Amar.
in the accuracy but may not be much, no?
No, Amar. In this paper, they do not do it, but this is something which could be tried, and we should definitely give it a try. Because if you look at the trigger tokens learned by the model, it doesn't make sense. What if, say, we at every stage, right? Once we learn these trigger tokens, we also rank them using, say, a language model, perplexity of the language model, so that there's minimal human intervention, hoping that.
Right. This is actually what I mean by language model based regularizer. Yeah. I think yeah. Okay.
Yeah, in this paper, they do not do that. So they want to push the boundary of what can be achieved with prompting. Even if the prompt obtained from the automated approach does not make sense, which gives the best results. So here they're clearly trying to push the boundaries of what we define as prompting.
Yeah. And also, this is very much dependent on the language model. So I understand the BERT might be the earlier one, which might have a lot of issues of biasing and all those things because of a small amount of data and so and so. But I think these things might change a lot when we go for the more recent models, which are like GPT-J,
Yeah,
OPT, Bloom. I think those things might might be starting making sense just by looking at the word itself. I don't know. This is what is my hunch.
yeah, so we'll have to take the results from this approach with a grain of salt, because this was a 2020 paper.
Yeah.
And yeah, so they mainly looked at BERT and Roberta model and not any other language models. So if we say apply auto prompting on GPT-3 or GPT-J or some of the recent models, do we observe something? Is the observation similar? That I'm not sure, but that's something interesting to see. Okay. So similar to earlier tasks, right? They also perform the task on fact retrieval, where you have the subject and they encode the relation as trigger tokens, and you have the masked token, and the masked token should generate the correct object. And even in this case, they compare it against manual prompting. So mean reciprocal rank with Llama manual prompting, it's 40.27, whereas auto prompting using 5 tokens or 7 tokens, they observe improvements. And similar observations are made irrespective of the model, whether it is BERT model or Roberta model. Okay. Now let's look at more into what kind of prompts the model learns. So this is a consolidation of the prompts learned by the model. For the sentiment analysis task, right? This is the prompt template which they have provided to the model sentence, the trigger tokens or the prompt template. I mean the prompts, and then P is the mass token. And the prompt found by the model is writing academics where overseas will appear. So irrespective of what the input sentence is, if I append the input sentence with this particular prompt token, I'll get the correct sentiment prediction. Similarly, for natural language inference, right, we have the premises, hypothesis, you have the premises, and then you have the match token, whether it is entailment, contradiction, or nothing. And you have the template tokens, sorry, the trigger tokens, and then the hypothesis. And the model discovers adding this trigger token, concrete pathic workplace, to the premise and hypothesis will more often than not lead to the current entailment prediction. The same goes for fact retrieval. X plays Y music, subject the trigger tokens, and P fireplace made antiques and alto.
Rudra,
And
do they show any ablation here by removing the sentence or premise after these targets have been generated?
no, Nihal.
Okay.
Yeah. So there are two things to look at it here, right? One is the prompt found by auto prompt, and also the label tokens. So for positive sentiment, the label tokens which they observe is partnership, extraordinary makes sense, but ashes blur, it doesn't really make sense. Similarly, for negative sentiment, words make sense, but persisted doesn't make sense. Unconstitutional,
Yeah, that's what I was thinking. Maybe they're overfitted by the target tokens, the prompts are being, like that has been generated.
yeah, but this is
Barely depend on the sentence at all.
yeah, near, but you'll have to see that they are also reporting the performance on the dev set and test set. They
Acha,
haven't seen any of the instances in the test set, and yet they're able to perform really well on the test set.
yes.
Yeah. So some more examples. So this is for relation extraction. Say works in the field of, the manual prompt is X works in the field of Y, whereas with auto prompt, they get X probability earliest fame total studying Y. This trigger token does not make much sense. With Roberta X 1830 dissertation applying Matsuki Y. Similarly, for relation 103, the native language of X is Y. X PA communal speaks proper Y. Okay, speaks makes as a some sense, but new optionally fluent traditional. So you see the kind of prompts learned by the model. So these prompts do not make sense when looking through the human eye, but that's what gives the best performance when we provide them as input to the language models. Okay. Yeah. Yeah. So in today's session, we looked at primarily two approaches on creating prompts. One approach looked at mining or paraphrasing, where you locate a very large corpus and try to extract prompts by providing some regular expressions or patterns, and show that instead of manually creating prompts, searching prompts on the large corpus definitely helps. And at the other extreme, we have approaches like auto prompt, which says that I don't want to search prompts. I let the model discover what is the best prompt for the task in hand. And a major limitation of such an automated approach is what we feel the best for language model does not make sense for humans. And another important point to focus is manual prompts always they give a lower bound on the performance of the model. So whatever we believe is the best might not be the best for the language model. So to conclude, yeah, the research community has also explored looking at continuous prompts, and we'll be talking more about continuous prompts or how to do prompt fine tuning. So that's an interesting thing which falls under the purview of fine tune, few short classification. We'll explore it in the next session, and also we'll look at some of the research, open research questions in the next session. Yeah, any questions? And these are the papers which I discussed today.
I have a question or discussion, unless anyone else has something to first.
Yes, sir.
Yeah, so should one even accept this as an acceptable scientific method? Some infinite capacity network has figured out some shortcuts in doing inference, and we're trying to understand from the outside without much influence on the training process itself what it has done. What it has done was guided by certain glue-like tasks,
Yes.
some mix of them, which may have had nothing to do with the specific prompt goals we have. And because of various tie-breaking and incomplete and insufficient training of certain word embeddings, we are basically getting this best performance with uninterpretable prompts. Great. So what?
Yes. Yeah. So when I was reading this paper made me uncomfortable. So
Glad
that's
to
why I
hear
wanted,
that.
yes,
Yeah.
and that's why I included this in my talk, so that we need to have some open discussions with respect to this, because where do we draw the line in search of the best performance?
So I have something to say here, Samit.
Sure.
So yeah, if we, let's say, look upon all these as black art and so on, and yeah, question, is there any scientific basis to this? Is it worth investigating this? Then maybe we'll have to also give up on understanding child development, child language acquisition, child psychology, because a child is also exposed to an enormous amount of visual and speech signals from the environment.
Yeah.
So isn't that analogous?
Oh, yes, there is an analogy there. But the child does not only learn from unstructured inputs. I am glad you made that comment, because I'm exactly proposing what we do to children. When we see children overfitting or misfitting data, we provide judicious training corrections, which I don't see enough of in the language model literature.
Yeah, there is a point there, judicious correction, of course. But no, I I do not completely agree with this point that we provide judicious training correction. Do we? I mean, we just expose the child to whatever the environment provides. It is nurture and nature combination, I would say. I don't know if I was audible.
You were audible. I think Savan sir has lost connectivity, I believe.
Yeah, possibly. Okay, so maybe Samuel lost his connectivity.
Can you hear me now?
Yeah, I can. Yeah.
Okay, great.
Could you hear me what I said?
Yeah, I heard you. So let me say that I don't know about the childhood of children nowadays, but when I was a child, I had to suffer through this giant red volume called Ren and Martin, right? So
It's a beautiful book, by the way.
yeah, I know. I mean, in retrospect, I can appreciate, and certainly NLP people will appreciate it more than me at that stage. But the point is that whatever wrong things I learned by overfitting or underfitting on random corpus that I read, right? So Three Investigators or Enid Blyton or Hardy Boys or what have you, right? I probably mislearned a lot of things, but that was cleaned up by forcing me to go through Ren and Martin.
So you are suggesting a regularizer, basically, which should be judicious.
Oh, I think all these language models should be regularized with a grammar book.
No, but by the way, linguistics actually despises prescriptive linguistics and favors descriptive linguistics. So some of the favorite examples are like, don't use double negative. But double negative is used quite a lot in many dialects of English.
As are double positives, like, yeah, right. So, and that's one case where two positives make a negative. If you say, yeah, right, you're actually refuting what is being said.
Yeah.
No, but I think this is a bit of a fashion, and even people who decree against prescriptive language teaching, I don't think they can deny the role of learning syntax properly.
And I think what plagues all these models is the complete mix-up of syntax and word knowledge.
Yeah, but what can you do really? Language model relies on huge amount of training corpus, and you train a large machine learning model with huge amount of corpus. You just expose a lot of language data, right?
So that's become the current working style. But I mean, who am I talking to? I mean, you did UNL before the rest of the world, so and that was an extreme act of let's keep things in control and keep things interpretable at all times, right? And I'm sure, despite the apparent sweeping success of neural methods, you have your soft corner for, and you're not alone. I mean, even Chris Manning is a bit torn between language by example alone versus language with inductive bias. So, and he has spent a lot of his career on like classical NLP stacks. And in the middle, around 2014 to 16, he tried building a bridge, but then the bridge got washed away. So, I mean, I think we should, I think the philosophical point is relatively clear to all of us, and we may have slightly different locations and positions about it. The question is, what is a good research program to launch to deal with it? So, for example, all these prompt hunting papers, none of them seem to give a very solid or authoritative prescription of changing the protocol with which language models are trained. They take that as a given. Should we be training these language models in a way that prompts become more transparent? I don't know. I'm not an expert in prompts. That's why I joined the talk.
No, but there is nothing to the training. You essentially do fill in the gap, right, by masking of tokens.
So I'm asking if that needs to change if we know that we are going to use the resulting language model for prompt-based action. And why not?
Okay, so we'll continue this very interesting topic.
Yeah, thanks.
Yeah. Okay, if there is any other point or question from anybody?
Sir, just a comment, Rob. So if we look at these examples here, so okay, one thing about this approach is at least we want to do the best in the end task. For example, I'm not so sure. Let's say if we do tenfold cross validation, we are going to get definitely different these trigger words every time. It looks like. So apart from data set, if I want to apply it in the wild, I'm not so sure how good it will perform. So yeah.
True, Sapan.
I don't know. Yeah.
So this paper, I mean, I did not choose this paper to show that like this is the best way to do prompting or prompt engineering. I wanted to, I brought this paper so that we can have a conversation about prompting. Where do we draw the line with respect to prompting? Because this clearly, this paper extends the definition of prompting, right? So instead of trying to come up with prompts which make sense to humans, I'll just let the model discover what the best prompt for the task in hand is, even though it doesn't make any sense to humans.
Right.
And also in some of the prompts, it doesn't make sense. There's no correlation with the task in hand too. Like why writing academics where overseas will appear influence the sentiment of the input sentence.
Yeah.
Okay, so we have another meeting. Thank you, Rudra. Thanks a lot. And next, after 2 weeks again, we'll continue, I suppose. Is that so, Amar? Are we continuing after this?
Yeah, sir.
Okay, fine. Okay, then thanks everybody. You have another
Thanks,
meeting.
everyone.
Thanks, Rudra. Thanks.
Thanks, everyone.